Welcome to Chapter 1 of our Chemical Engineering Fluid Mechanics series, Fluids, Pressure, and Statics. The subtitle tells you where we are going: density, viscosity, and the pressure field. This chapter lays the groundwork for the whole series. What makes a fluid, which two properties the subject runs on, how pressure is distributed in a fluid at rest, and how a mass balance for a pipe becomes the continuity equation. Our Chemical Engineering Introduction series introduced transport phenomena, where momentum, heat, and mass all obey laws of the form flux equals coefficient times driving force. This series develops the first row of that table, momentum transport. Momentum comes first because its driving force, a velocity gradient, is the one you can actually see. Across these 10 slides, you will learn to define a fluid by its response to shear, state Newton's law of viscosity, compute hydrostatic pressure, distinguish gauge from absolute pressure, explain buoyancy and gravity separation, and apply continuity in both its mass flow and incompressible forms. Walk a chemical plant and count what is standing still. Almost nothing is. Feeds are pumped, gas is compressed, vapor climbs a distillation column while liquid runs back down, cooling water loops through exchangers, and product leaves in a pipeline. A plant is, mechanically, a machine for moving fluids while something useful happens to them on the way. That pays in 3 currencies. First, pressure drop is money. Every meter of pipe, every bend and valve takes a bite out of the pressure, and a pump or compressor puts it back, on the electricity bill, for the life of the plant. The cost scales steeply with velocity, as Chapter 4 makes quantitative. Second, flow regime decides performance. Whether flow is smooth and layered or chaotic and mixing, the subject of Chapter 3 changes heat transfer coefficients by an order of magnitude and controls whether reactants ever meet. Third, safety lives here. Overpressure, water hammer, cavitating pumps, and blocked-in lines are fluid mechanics problems first. A solid under a shear stress, meaning a force applied parallel to a surface, deforms by a fixed amount and then stops. A fluid cannot. Apply any shear stress, however small, and it keeps deforming as long as the stress lasts. That continuous deformation is flow, and it is the definition. A fluid deforms continuously under shear. Liquids and gases both qualify, differing mainly in compressibility. 2 properties carry almost all the weight here. Density, mass per unit volume in kilograms per cubic meter, sets what a fluid weighs, what pressure a column of it generates, and how much momentum a stream carries. Viscosity, resistance to shearing in Pascal seconds, sets the force needed to keep it moving. At about 20 degrees Celsius, water is roughly 998 kilograms per cubic meter and 1 millipascal second. Air at 1 atmosphere is about 1.2 kilograms per cubic meter. Honey is of order 10 Pascal seconds. Read those for ratios, not digits. Liquid densities cluster within a factor of 2 of water, and gases are about 1,000 times lighter. Heating a liquid thins it, heating a gas thickens it slightly. Picture a fluid between 2 parallel plates, the lower one fixed and the upper one dragged sideways at steady speed. The layer touching each plate moves with it. That is the no-slip condition, an experimental fact underpinning the whole subject, and it means a linear velocity profile develops across the gap. The shear stress sustaining that profile is tau equals mu times dv by dy, the viscosity times the velocity gradient. This is the transport table made concrete. A momentum flux, tau in newtons per square meter, equals a coefficient, the viscosity, times a driving force, the velocity gradient. Momentum diffuses from fast layers into slow ones exactly as heat diffuses from hot to cold. Fluids obeying this law with constant viscosity are Newtonian: water, air, most solvents. Many industrial fluids are not. Shear thinning materials, such as polymer solutions, paints, and many slurries, thin out as you shear them harder, which is why a stirred slurry pumps more easily than its at rest thickness suggests. This series is Newtonian throughout, so the later correlations do not apply to a non-Newtonian fluid as written. Pressure is a normal stress, force per unit area in pascals. In a fluid at rest, it is isotropic, meaning the same magnitude in every direction at a point, so sensor orientation does not matter. The only thing that changes it is depth, because the fluid below must hold up the weight of the fluid above. That gives delta P equals rho GH, with density in kilograms per cubic meter, G of 9.81 meters per second squared, and H the vertical depth in meters. Note what is absent: vessel shape, cross-sectional area, and total quantity of liquid. A narrow standpipe and a wide tank filled to the same height read the same pressure at the bottom. For water at 20 degrees Celsius, 10 meters down gives 998 times 9.81 times 10, which is 97,904 pascals, about 0.979 bar or 0.966 atmospheres. Hence the working rule of thumb: 10 meters of water is roughly 1 atmosphere, or roughly 1 bar. Exactly, 1 atmosphere of water head is 10.35 meters, and 1 bar is 10.21 meters, so the rule is good to about 3.5%. Absolute pressure equals gauge pressure plus atmospheric pressure. Nearly every pressure instrument in a plant reads gauge pressure, the difference from local atmosphere, reported as barg, kilopascals gauge, or sig. A vessel showing 0 is at atmospheric pressure, not vacuum. Other calculations demand absolute pressure: the ideal gas law, compressor work, vapor pressure comparisons, and any system below atmospheric. The confusion is a chronic source of real errors. Reading 2 barg as 2 bara is a 50% error in a gas's absolute pressure, hence in its density, and hence in the compressor duty computed from it. State the convention in every calculation you write. A worked case makes the arithmetic concrete. A gauge on a water tank base reads 0.78 bar, and taking atmospheric as 1.013 bar, the absolute pressure there is 1.79 bara. Now seal that tank and pressurize its vapor space to 2 barg. Because pressure applied at the surface is transmitted undiminished throughout the fluid, the base gauge reads 2 plus 0.78, which is 2.78 barg, or 3.79 bara. 2. Everyday uses follow directly from delta P equals rho GH. A manometer turns a pressure difference into a readable height difference in a liquid column. Delta P equals rho G delta H run the same relation backward, and it measures most tank levels. A differential pressure transmitter compares the bottom of a vessel with the vapor space above it, and reports H equals delta P divided by rho G. The catch is in the equation. The reading is only as good as the assumed density, so a shift in temperature, composition, or entrained gas moves the indicated level while the real one holds still. The chapter's code makes the warning concrete. The same 50 kilopascal reading is 5.11 meters of water at 998 kilograms per cubic meter, 6.37 meters of a light organic at 800, or 4.25 meters of brine at 1200. Calibrate a transmitter for the wrong fluid, and it confidently reports a level off by 20% or more. A tank rated for 8 meters would appear nearly full while holding only 6 meters of brine. That is a calibration error, not an instrument fault. Because pressure increases with depth, a submerged object is pushed harder from below than from above, and the imbalance is an upward force. Archimedes' principle states its size. The buoyant force equals the weight of fluid displaced, Fb equals rho fluid times g times v. Denser than the surrounding fluid, an object sinks. Lighter, it rises. That single comparison explains a whole equipment category. The lighter phase rises, giving bubbles in a column, an oil layer in a decanter, and froth flotation. The denser phase settles, giving catalyst fines in a settler, crystals in a thickener, and sludge in a clarifier. Gravity separation is the cheapest separation there is, needing no energy beyond residence time. How fast it moves follows from 3 forces: gravity down, buoyancy up, and drag opposing the motion. Drag grows with speed, so they balance quickly, and the particle travels at a constant terminal velocity. For small particles moving slowly, the Stokes regime applies. Terminal velocity rises with the density difference and the square of particle size, and falls as the continuous phase's viscosity rises. doubling particle diameter speeds, settling roughly fourfold. The introduction series wrote every balance as accumulation equals in minus out plus generation minus consumption. For mass flowing through a pipe, nothing is generated or consumed, and at steady state nothing accumulates, so what enters must leave. That gives the continuity equation, the mass balance of fluid mechanics. Mass flow rate equals rho VA, held constant, where V is the average velocity over the cross-section and A is the flow area. For an incompressible fluid, meaning any liquid, or a gas whose pressure changes only modestly along the line, density is equal at both ends and cancels, leaving V1 a 1 equals V2 a 2. Take a pipe carrying liquid at 2 meters per second that steps down from 100 to 50 millimeters internal diameter. Area scales with diameter squared, so having the diameter quarters the area, and continuity demands the velocity rise fourfold to 8 meters per second from geometry alone. Pipe sizing then trades steel against pumping power. As common design guidelines, not physical laws, process liquids run about 1 to 3 meters per second, and gases and vapors about 15 to 30. Let's pull the chapter together. A fluid deforms continuously under any shear stress, and this series runs on two properties. Density, about 998 kilograms per cubic meter for water and about 1.2 for air, and viscosity, about 1 millipascal second for water and of order 10 pascal seconds for honey. Newton's law of viscosity, tau equals mu times the velocity gradient, is momentum transport in flux equals coefficient times gradient form. Newtonian fluids have constant viscosity. Shear thinning polymer solutions and slurries do not. Pressure is an isotropic normal stress set only by depth, delta P equals rho GH, and a 10-meter water column gives 97,904 pascals, about 0.979 bar, which is the rule of thumb that 10 meters of water is roughly 1 atmosphere, good to about 3.5%. Instruments read gauge, gas law, and compressor calculations need absolute. Level by differential pressure is only as accurate as the assumed density. Buoyancy makes density difference the driver of decanters, settlers, and flotation. Continuity gives V1 a 1 equals V2 a 2. Next chapter, Bernoulli and the mechanical energy balance. Welcome to Chapter 2 of our Chemical Engineering Fluid Mechanics series, Bernoulli and the mechanical energy balance. The subtitle tells you where we are going, where the energy of a flow goes. Chapter 1 left the fluid standing still. This chapter sets it moving and follows its energy. How pressure, speed, and elevation trade against one another, how that trade becomes a flow measurement, and what friction takes away permanently. The Chemical Engineering Thermodynamics series opened with the first law for a flowing stream, delta H equals Q minus shaft work, and deliberately dropped the kinetic and potential energy terms as negligible. In fluid mechanics, those are exactly the terms we care about, and the thermal ones are what we set aside. Across these 10 slides, you will write Bernoulli's equation as an energy balance per kilogram and state its assumptions. Apply Torricelli's result to a draining tank. Explain how Venturi meters, orifice plates, and Pitot tubes turn a pressure difference into a flow rate. Extend Bernoulli into the mechanical energy balance with friction loss and pump work, and recognize the conditions that cause cavitation. Take a fluid of constant density with no heat exchange, no shaft work, and for now no friction. What remains is a balance of mechanical energy alone. Per kilogram of fluid, three quantities can hold it, P over rho plus V squared over 2 plus GZ, and their sum is constant. This is Bernoulli's equation. Every term has units of joules per kilogram, and that shared currency is the whole point. The three forms are interconvertible, and a flow moves energy freely among them. P over rho is pressure energy, also called flow work, the energy carried by the fluid because it is pressurized. V squared over 2 is kinetic energy, the energy of motion. And GZ is potential energy, the energy of elevation above a chosen datum. Because the sum is constant along a streamline, any gain in one term is paid for out of the others. Speed a fluid up and its pressure falls. Raise it and, at constant speed, its pressure falls by rho gz. Nothing is created here. The accounting simply moves from one column to another. Now put numbers on the three terms for water, because they set intuition for the rest of the series. 1 bar of pressure energy is 10 to the 5th divided by 998, which is 100 joules per kilogram. 10 meters of elevation is 98.1 joules per kilogram. But 2 meters per second, an entirely ordinary pipe velocity, gives only 2 joules per kilogram. Read that carefully. At ordinary pipe velocities of 1 to 3 meters per second, the kinetic term is tiny, a couple of joules per kilogram, about 0.02 bar. Elevation is far larger. 10 meters of water is worth roughly 1 bar. So pressure dominates a pumped system, and kinetic energy becomes interesting only where the fluid is deliberately accelerated, which is precisely what a nozzle, an orifice, or a leaking flange does. The assumptions behind Bernoulli are strict and worth stating aloud, because every real application violates at least one. Steady flow, constant density, no friction, no shaft work, and along a single streamline. Bernoulli is therefore a reasoning tool and a first estimate, not a design equation. The classic application is a vented tank with a hole in its side, which every plant contains as a drain or a leak. Apply Bernoulli between the free liquid surface and the jet leaving the hole. Both are open to atmosphere, so the pressure terms cancel. The tank is wide compared with the hole, so its surface velocity is about 0. Taking the hole as the datum, gh equals v squared over 2, so v equals the square root of 2gh, that is Torricelli's result. For a liquid level of 5 meters above the hole, v is the square root of 2 times 9.81 times 5, the square root of 98.1, which is 9.9 meters per second. That is identical to the speed of an object dropped from the same height. Note also what is absent: density. Ideal draining is equally fast for water, kerosene, and mercury. Reality is slower on 2 counts: friction at the hole edge and the vena contracta, the jet contracting after it leaves the wall. Both are lumped into a discharge coefficient, typically about 0.6 to 0.65 for a sharp-edged orifice. Bernoulli earns its keep in instrumentation. Squeeze a pipe and continuity forces the fluid to speed up through the smaller area. Bernoulli then says the pressure must drop to pay for it. Measure that drop and you have inferred the flow rate without ever putting a moving part in the stream. 3 devices do this. An orifice plate is a drilled plate clamped between flanges. Its permanent pressure loss is high, typically 50 to 80% of the measured delta P, but it is cheap, easy to replace, and by far the most common. A venturi is a gradual convergence, a throat, and a long, gentle diffuser. Its permanent loss is low, typically 10 to 20%, but it is expensive and bulky, used where pumping cost or available head matters. Its long, tapered outlet lets the flow decelerate smoothly and recover most of its pressure, while the orifice dumps its jet into a sudden expansion where the fluid churns. A pitot tube faces into the flow with negligible loss, but it measures local velocity at one point, not total flow. Combining continuity and Bernoulli for a constriction gives the working equation used by every differential pressure flow meter. Q equals CD times the square root of 2 delta P over rho. As written, this form drops the velocity of approach factor, which is acceptable when the bore is much smaller than the pipe, but it is a correction a real meter calculation carries explicitly. The chapter's code runs a 50 mm orifice bore with a discharge coefficient of 0.62, typical for a sharp-edged orifice plate. Sweep the differential pressure, and the characteristic weakness of every such meter appears. The relationship is square root, not linear. Quadrupling delta P from 5 to 20 kilopascals only doubles the flow, from 13.87 to 27.75 cubic meters per hour. Near the bottom of the range, a large fractional error in delta P becomes a large error in Q. That is why an orifice meter is normally trusted over a turndown, meaning the usable ratio of maximum to minimum flow, of only about 3 to 1 or 4 to 1. Operate a plant far below design rate, and its flow measurements quietly become unreliable. Bernoulli's frictionless fluid does not exist. Real flow rubs against pipe walls and against itself, and that rubbing removes mechanical energy from the balance. Adding a loss term HF and the work supplied by a pump gives the mechanical energy balance, the equation the rest of this series is built on. P1 over rho plus V1 squared over 2 plus GZ1 plus pump work equals P2 over rho plus V2 squared over 2 plus GZ2 plus HF. All terms are joules per kilogram. Two asymmetries deserve attention. Pump work appears only on the left because a pump adds mechanical energy, and it is the only thing in the equation that can. And HF appears only on the right and is always positive, never negative, no matter which way the fluid goes. Reverse the flow direction and friction still takes its cut. The friction and shaft work that Bernoulli left out are now carried by exactly those two terms, and that is what turns a reasoning tool into an equation you can design with. That one-sidedness is the second law showing up in a pipe. The energy removed by friction is not destroyed. It reappears as internal energy, warming the fluid by a fraction of a degree, and the first law is satisfied exactly. But the conversion runs one way only. Warm water does not spontaneously reorganize itself into pressure. So friction converts mechanical energy into internal energy, and that is the second law at work. Thermodynamics Chapter 2 calls this destroyed work potential, and every real flow generates entropy. Friction degrades energy quality while conserving its quantity. Practically, this is where design leverage lives. Everything else in the mechanical energy balance is fixed by the job, the tank is where it is, and the pressure is what the process needs. Only HF follows from design choices, namely pipe diameter, length, fittings, and roughness. That is why HF sizes the pump and sets the electricity bill. Chapter 4 is devoted entirely to computing it, and Chapter 5 to paying for it. The mechanical energy balance also warns of a specific failure. Follow the pressure along a line into a pump suction. Elevation losses, friction, and acceleration into the pipe all subtract from it. If the local pressure anywhere falls to the liquid's vapor pressure, the pressure at which it boils at that temperature, the liquid vaporizes in place. Vapor bubbles form, are swept into the higher pressure region of the impeller, and collapse violently. That collapse is cavitation. It sounds like gravel in the casing, erodes impeller metal, wrecks bearings and seals, and destroys the pump's delivered head, a leading cause of pump failure in plants. Two design rules follow directly, and both concern the suction side. Short, less pipe length means less HF subtracted before the fluid reaches the impeller. Fat, a larger diameter means lower velocity, which cuts both the friction loss and the V squared over 2 drawn out of the pressure term. Temperature narrows the margin further. Water at 25 degrees Celsius boils at about 3.2 kilopascals absolute, but at 80 degrees, its vapor pressure is roughly 47 kilopascals, leaving under 6 meters of head to spend. Let's pull the chapter together. Bernoulli's equation, P over rho plus V squared over 2 plus GZ equals a constant in joules per kilogram, balances mechanical energy per kilogram of ideal flow, and the three terms are interconvertible, so a gain in one is paid for by the others. Magnitudes set in tuition. 1 bar is about 100 joules per kilogram, and 10 meters of elevation about 98 joules per kilogram, but 2 meters per second is only about 2, so kinetic energy matters only where the fluid is deliberately accelerated. Torricelli gives 9.9 meters per second under 5 meters of head, independent of density, with a discharge coefficient of typically 0.6 to 0.65 for a sharp orifice. Q equals CD at times the square root of 2 delta P over rho underlies orifice plates, which permanently lose 50 to 80%, venturis at 10 to 20%, and pitot tubes for local velocity, with turndown limited to about 3 or 4 to 1. The mechanical energy balance adds pump work and HF, which is always positive. Next chapter, laminar and turbulent flow, and the Reynolds number. Welcome to Chapter 3 of our Chemical Engineering Fluid Mechanics series, Laminar, Turbulent, and the Reynolds Number. The subtitle tells you where we are going: two regimes, one dimensionless group. Chapter 2 balanced mechanical energy along a streamline and left one term deliberately vague: the friction loss. Before that loss can be given a number, the flow itself must be classified, and the classification rests on a single dimensionless group. Across these 10 slides, we build that classification from the experiment that revealed it. We start in 1883 with Osborne Reynolds and a thread of dye in a glass pipe, form the Reynolds number from density, velocity, diameter, and viscosity, and use it to sort pipe flow into laminar, transitional, and turbulent. Then we look at what life is like inside each regime: the parabolic profile and the Hagen-Poiseuille law on the laminar side, eddies and vigorous mixing on the turbulent side. By the end, you will be able to compute a Reynolds number, classify a flow, explain why industry runs turbulent almost everywhere it can, and generalize the same group to tanks, packed beds, and settling particles. In 1883, Osborne Reynolds ran water from a tank through a straight glass pipe and injected a fine jet of dye on the center line. At low flow rates, the dye drew a straight, sharp thread the whole length of the pipe. The water was moving in orderly layers that slid past one another without exchanging material sideways. Opening the valve further changed nothing, until quite abruptly it changed everything. Past a certain flow rate, the thread wavered, broke up, and dispersed across the whole cross-section within a few pipe diameters. He had not blurred one regime into the other. He had crossed a threshold between two qualitatively different states of motion. The decisive result came next. He repeated the experiment with different diameters, with different temperatures, which changed the viscosity, and with different liquids, and the velocity at which the thread broke up moved around wildly. Yet when those four variables were combined into a single dimensionless group, transition always occurred near the same value of it. That number now carries his name. The Reynolds number is density times velocity times diameter, divided by viscosity. Density is in kilograms per cubic meter, velocity is the average velocity in meters per second, diameter is the pipe inside diameter in meters, and the dynamic viscosity is in Pascal seconds. The group is a ratio of inertial to viscous forces. The numerator measures the fluid's tendency to keep doing what it is doing. The denominator measures its ability to damp a disturbance by internal friction. When viscosity wins, perturbations die and the layers stay ordered. When inertia wins, a perturbation feeds on the flow's own momentum, grows, and order collapses. It is worth checking once that the group is genuinely dimensionless, because that is what lets one threshold serve both a laboratory tube and a refinery line. For flow inside a circular pipe, the standard textbook guideline is this: laminar below about 2,100, transitional between about 2,100 and 4,000, and fully turbulent above about 4,000. These are engineering guidelines, not physical constants. The lower value is quoted variously as 2,100 or 2,300, and designers avoid sizing lines into the transitional band. Two numbers make the guideline concrete. First, water, density 998 kilograms per cubic meter, viscosity 0.001 Pascal seconds, moving at 2 meters per second through a 0.05 meter pipe. The Reynolds number is 998 times 2 times 0.05, divided by 0.001, which is 99,800, or about 1 times 10 to the fifth. That is turbulent, 25 times above the threshold, and it is the industrial norm. Water-like fluids at ordinary velocities in ordinary pipes are turbulent, and making them otherwise takes deliberate effort. Second, a viscous oil, density 900 kilograms per cubic meter, viscosity 0.1 Pascal seconds, 100 times water's, moving at 0.5 meters per second through the same 0.05 meter pipe. The Reynolds number is 900 times 0.5 times 0.05, divided by 0.1, which is 225. Laminar, and not marginally so. Heavy oils, syrups, polymer melts, and concentrated slurries live here permanently. Notice that the pipe is identical in both cases. The regime was decided by the fluid and the velocity, not by the hardware. In laminar flow, the fluid moves as concentric cylindrical shells sliding over one another, with molecules crossing between shells only by slow diffusion. The wall holds its adjacent layer at zero velocity, the no-slip condition. Each layer drags on the next through viscosity, and the result is a parabolic velocity profile, zero at the wall and maximum on the axis. For a circular pipe, the centerline velocity is exactly twice the average. Centerline fluid, therefore, reaches the outlet in half the average time while fluid near the wall crawls, which gives a laminar tubular reactor a wide spread of residence times. The pressure drop sustaining laminar pipe flow is the Hagen-Poiseuille equation. Delta P equals 32 times viscosity times length times velocity divided by diameter squared. Note what is absent from it. There is no density, and there is no roughness. Laminar friction is pure viscous shear. And the equation is valid in the laminar regime only. Applying it to turbulent flow is a common error, and it underpredicts badly. The diameter squared in Hagen-Poiseuille looks like a modest penalty for narrowing a pipe, but it understates the truth, because the real comparison is at fixed volumetric flow rate, not at fixed velocity. The same flow through a smaller pipe means faster fluid. Velocity is the flow rate divided by area, which is 4q over pi d squared, so velocity scales as 1 over diameter squared. Substitute that into Hagen-Poiseuille, and the two effects compound. Pressure drop becomes 128 times viscosity times length times flow rate, divided by pi times diameter to the fourth. Having the diameter at fixed flow rate multiplies velocity by 4 and pressure drop by 2 to the fourth, which is 16. Cutting it to 1/3 multiplies pressure drop by 81. Pumping power is pressure drop times flow rate, so operating cost follows the same fourth power. Keep the bases straight. At fixed velocity, the formula gives only diameter to the -2, a factor of 4, and quoting 4 instead of 16 is the mistake to avoid. It comes from forgetting that a narrower pipe also runs faster. Turbulent flow contains eddies, swirling fluid parcels across a wide range of sizes, the large ones drawing energy from the mean flow and breaking into smaller ones until viscosity dissipates it as heat. At any fixed point, the velocity fluctuates continuously about a mean. Eddies transport momentum across the pipe far more effectively than molecular viscosity can, so the mean profile is flattened, nearly uniform across the core, with the whole velocity change compressed into a thin layer near the wall. The centerline exceeds the average by only about 20%, against the factor of 2 in laminar flow. Industry mostly runs turbulent by choice. Mixing needs cross-stream transport, and laminar flow has essentially none. Heat transfer at a wall depends on how fast wall fluid is swept into the bulk, and eddies do this orders of magnitude faster than conduction. Mass transfer, meaning dissolution, absorption, and extraction, obeys the same logic. Turbulence is what makes process equipment compact. The price is friction. Turbulent pressure drop rises roughly with the square of velocity rather than linearly, so the pumping bill grows faster than throughput. Laminar flow keeps genuine niches. Microfluidics runs at Reynolds numbers of order 1 or below, where two streams flow side by side in a channel and mix only by diffusion. That is a nuisance to engineer around, or a feature to exploit in a diffusion-based assay. Highly viscous fluids, such as polymer melts, greases, and food pastes, cannot reach turbulence at any practical velocity, so they must be moved laminarly and mixed mechanically. Laminar flow reactors and coating operations use the ordered profile deliberately. The chapter's exercise puts a number on the viscous case. Take a glycerol-like fluid, density 1260 kilograms per cubic meter and viscosity 1 pascal seconds, flowing at 1 meter per second through an 80 millimeter pipe. Its Reynolds number is about 101, firmly laminar. To reach 2100, it would have to travel at 20.8 meters per second. Liquid lines are designed around 1 to 3 meters per second, so 20.8 would mean enormous pressure drop, erosion, and noise. Viscous fluids essentially never go turbulent in pipes. They must be designed as permanently laminar systems. Nothing in the reasoning behind the Reynolds number is specific to a pipe. The group compares inertia with viscosity, and forming it needs only a characteristic length and a velocity appropriate to the geometry. What does not transfer is the numerical threshold, because the length is defined differently in each case. For pipe flow, the length is the inside diameter, and the guideline is laminar below 2,100 and turbulent above 4,000. For a stirred tank, the Reynolds number is density times impeller speed in revolutions per second times impeller diameter squared over viscosity, and it is laminar below about 10 and turbulent above about 10,000. For a packed bed, the length is the particle diameter, and the velocity is the superficial velocity, the volumetric flow divided by the full cross-section as if no packing were present. For flow past a particle, it is again the particle diameter, and Stokes' law is valid only below a Reynolds number of about 0.1 to 1. That last row connects back to Chapter 1. Always check the particle Reynolds number after computing a settling velocity, and always state which Reynolds number you mean. Let's pull the chapter together. Reynolds' 1883 dye experiment showed two distinct regimes, not a gradual blur. A straight dye thread breaking up abruptly into full pipe dispersion. One dimensionless group sets the transition, the Reynolds number, density times velocity times diameter over viscosity, the ratio of inertial to viscous forces. All units cancel, which is why one threshold serves laboratory and plant alike. The pipe guideline is laminar below about 2,100 and fully turbulent above about 4,000, with a transitional band that designers avoid. Water at 2 meters per second in a 0.05 meter pipe gives 99,800, turbulent and typical. A viscous oil at 0.5 meters per second gives 225, laminar. Laminar flow has a parabolic profile with centerline velocity twice the average and obeys Hagen-Poiseuille, in which neither density nor roughness appears. At fixed volumetric flow rate, having the diameter multiplies pressure drop by 16, not by 4. Turbulence flattens the profile and mixes vigorously, and industry pays for that in friction. Next chapter, pipe flow and pressure drop. Welcome to Chapter 4 of our Chemical Engineering Fluid Mechanics series, Pipe Flow and Pressure Drop. The subtitle tells you where we are going, the friction factor, and the cost of moving fluid. This chapter turns the friction term that Chapter 2 left as a symbol into a number. The Darcy-Weisbach equation and the friction factor let you compute what a pipe run costs to pump, and the answer scales so steeply with diameter that it decides the size of nearly every line on a flowsheet. Across these 10 slides, we start by framing pressure drop as an operating cost rather than a modeling detail. Write Darcy-Weisbach and settle the Darcy versus Fanning convention before it can hurt anyone. Show that the laminar friction factor is Hagen-Poiseuille in disguise, read the Moody chart conceptually, and then work a complete design example from velocity through pascals to kilowatts. By the end, you will be able to compute pressure drop and pumping power for a pipe run, account for fittings and valves, and explain why the economic diameter sits where it does. The mechanical energy balance of Chapter 2 ended with a term written HF, the friction loss, and a promise that it would later be computed rather than assumed. That term is not an accounting nuisance. It is a bill. Friction converts mechanical energy into heat that never comes back. Whatever the fluid loses to the pipe wall, a pump must put back in, and the motor driving that pump draws electricity every hour the plant runs. A line that wastes half a kilowatt costs about 4,400 kilowatt-hours a year in continuous service, for one line, in a plant that has thousands of them. The capital cost of a pipe is paid once. Its friction is paid forever. That framing sets up the design question of this chapter. A larger pipe carries the same flow at a lower velocity, and lower velocity means dramatically less friction, but larger pipe costs more steel, more supports, and more welding. A smaller pipe is cheap to buy and expensive to operate. Somewhere between sits the diameter that minimizes the sum, and finding it requires a quantitative model of friction, the friction factor. The working equation for frictional pressure drop in a straight run of circular pipe is Darcy-Weisbach. Pressure drop equals the friction factor times length over diameter times rho v squared over 2. Pressure drop is proportional to length, inversely proportional to diameter, and proportional to the velocity head, rho v squared over 2, the same kinetic energy group that ran through Bernoulli's equation. Doubling the velocity quadruples the loss at fixed friction factor. Now the warning. 2 friction factors are in circulation, and they differ by a factor of 4. The Darcy factor is 4 times the Fanning factor. This series uses the Darcy factor, also called the Moody factor, throughout, the one for which the laminar result is 64 over the Reynolds number. Some chemical engineering texts use the Fanning factor, for which the laminar result is 16 over the Reynolds number, and the equation carries an explicit 4. Mixing them produces a pressure drop wrong by 4 times. Always check what a chart, a correlation, or a piece of software returns. The quickest test is the laminar line. 64 means Darcy, 16 means Fanning. In laminar flow, the friction factor is not an empirical quantity at all. It is exact. F equals 64 divided by the Reynolds number. This is Chapter 3's Hagen-Poiseuille law rewritten. That law gives pressure drop as 32 times viscosity times length times velocity over diameter squared. Substitute it into Darcy-Weisbach and solve for F. The length cancels, 1 power of diameter cancels, and what remains is 64 times viscosity over density times velocity times diameter, which is exactly 64 over the Reynolds number. Same physics, 2 notations. Notice a second thing while we are here. Laminar pressure drop is proportional to velocity, not to velocity squared, because the v squared sitting in Darcy-Weisbach is undone by the 1 over v hidden inside the friction factor. Notice a third. Roughness appears nowhere in this result. In laminar flow, the fluid never feels the wall texture, so smooth pipes and rough pipes fall on the same line. In turbulent flow, no such derivation exists, and the friction factor becomes an experimental correlation. In turbulent flow, the friction factor is a correlation in 2 dimensionless groups, the Reynolds number and the relative roughness, the height of the wall's surface irregularities divided by the pipe diameter. A small bump matters in a 10 mm tube and is invisible in a 1 meter header, which is why the ratio, not the absolute height, governs. Commercial steel carries a standard design roughness of about 0.045 millimeters. Drawn copper or glass tubing is effectively smooth at about 0.0015. Galvanized iron is about 0.15. Concrete, from about 0.3 to 3 millimeters. The classical way to obtain the friction factor is the Moody chart. At low Reynolds number there is a single steep straight line, and all pipes fall on it. Past transition, the curves fan out by relative roughness and then flatten to the right. In that fully rough regime, the friction factor no longer depends on Reynolds number at all and is set by relative roughness alone. Nobody reads the value off paper anymore. Software solves Colebrook's implicit correlation or the explicit Swamy-Jane approximation, which reproduces it to within about 1%. Take water at 998 kilograms per cubic meter flowing at 2 meters per second through a commercial steel line of 0.05 meters inside diameter, over 100 meters of length. From Chapter 3's definition, the Reynolds number is about 1 times 10 to the 5th, firmly turbulent, and we take the typical value of 0.02 for the friction factor. Be honest about that rounding. The Swamy-Jane correlation actually gives 0.022 here, so 0.02 understates the pressure drop by about 10%, but it makes for a clean hand calculation. Pressure drop is 0.02 times 100 over 0.05 times 998 times 2 squared over 2, which is 0.02 times 2000 times 1996, or 79,840 pascals, about 0.8 bar. Now convert that to money. The volumetric flow is velocity times area, 0.003927 cubic meters per second. Hydraulic power, the mechanical power the fluid actually absorbs, is flow rate times pressure drop, 313.5 watts, about 0.31 kilowatts. A pump does not deliver that for free. At a typical combined pump and motor efficiency of 65%, the electrical draw is about 0.48 kilowatts, roughly 4,200 kilowatt-hours a year in continuous service. Now change the diameter while holding the flow rate fixed. At fixed volumetric flow, velocity scales as 1 over diameter squared, because the area goes as diameter squared, so velocity squared scales as diameter to the -4. Combine that with the explicit 1 over d already in Darcy-Weisbach and pressure drop scales as diameter to the -5. Since the flow rate is fixed, pumping power scales the same way. Having the diameter multiplies the pumping power by 32. Check it against the worked example. Keep the same 0.003927 cubic meters per second and the same friction factor, but open the pipe from 0.05 to 0.1 meters. The area quadruples, so velocity falls to 0.5 meters per second, and the pressure drop becomes 0.02 times 1,000 times 124.75, which is 2,495 pascals, about 0.025 bar. The ratio is 79,840 over 2,495, which is exactly 32, precisely the 2 to the 5th the law predicts. Hydraulic power falls from 313.5 watts to 9.8 watts. In reality, the improvement is slightly smaller, because doubling the diameter shifts the true friction factor a little, but the 5th power scaling dominates any such correction. Real piping bends, branches, expands, contracts, and passes through valves, and every one of those features costs pressure. 2 equivalent bookkeeping methods are in use. The K-factor, or velocity head, method assigns each fitting a dimensionless loss coefficient and charges it against the velocity head. Pressure drop equals K times rho v squared over 2. The equivalent length method instead expresses each fitting as the length of straight pipe causing the same loss, an elbow equal to 30 diameters, say, and adds it to the length before applying Darcy-Weisbach once. The two are the same statement rearranged. Ranking the common items, a long radius elbow is small, and a short radius elbow costs noticeably more. A T taken through the run is nearly free. A gate valve fully open is small, because it is designed for isolation with an open bore. A globe valve fully open is large, often tens of times a gate valve, because of its tortuous internal path. A control valve is large by design. Control valves work precisely by throttling, by consuming pressure drop. Control engineers call this valve authority, and controllability is bought with energy, permanently. Which returns us to the economic velocity heuristic of Chapter 1, roughly 1 to 3 meters per second for liquid lines. That range is not a fluid mechanical constant. It is the observed location of a cost minimum. Below it, you are buying steel you do not need. Above it, the 5th power law takes over, and you pay an electricity bill for decades. At 25 millimeters, the line demands over 15 kilowatts of electricity. At 100 millimeters, it demands 15 watts. The pipe is 4 times the diameter, and perhaps 6 or 8 times the cost per meter, and it has cut the operating cost by a factor of 1,000. That is why the 5th power matters more than almost any other exponent in process engineering. It is also why nobody simply specifies the largest available pipe. Capital rises without limit, while the absolute power saving eventually becomes negligible. Duty cycle moves the optimum too. Continuous service pushes toward larger pipe. This is exactly the trade-off that sets the reflux ratio in the introduction series. Buy the equipment once, or pay the utility every hour. Let's pull the chapter together. Frictional pressure drop is an operating cost, not a modeling detail. A pump replaces the lost energy every hour the plant runs, so pipe capital is paid once and friction is paid forever. Darcy-Weisbach gives pressure drop as the friction factor times length over diameter times rho v squared over 2, proportional to length, inverse in diameter, proportional to the velocity head. This series uses the Darcy or Moody factor. The Darcy factor is 4 times the fanning factor, and mixing them gives an answer wrong by 4. Check the laminar line. 64 means Darcy, 16 means fanning. In laminar flow, the friction factor is exactly 64 over the Reynolds number, algebraically identical to Hagen-Poiseuille. In turbulent flow, it is empirical, typically 0.02 to 0.04 for commercial steel. The worked case gives 79,840 pascals, about 0.8 bar, a hydraulic power of about 0.31 kilowatts, and about 0.48 kilowatts electrical at a typical 65% efficiency. At fixed flow rate, having the diameter multiplies pumping power by 32. Next chapter, pumps and piping systems. Welcome to the 5th and final chapter of our Chemical Engineering Fluid Mechanics series, Pumps and Piping Systems, or Matching the Machine to the Circuit. Chapter 4, Counted the Cost of Moving Fluid Through Pipe. Today we meet the machine that pays that bill. Across these 10 slides, we will define what a pump supplies to the mechanical energy balance, see why industry quotes head in meters rather than pressure in bar, and separate the two families of pump that a chemical plant runs on. We will find the operating point, the single flow rate where a pump curve meets a system curve, and compare the two ways of moving that point, a throttling valve and a variable speed drive. We will put numbers on the difference between them. We will check a suction line for cavitation using the net positive suction head criterion, look briefly at what changes when the fluid is a gas, and then close the series. Let us begin. Chapter 2 wrote the mechanical energy balance with a term for shaft work and left it as a promise. Chapter 4 then made that promise expensive. Friction in pipes, fittings, and valves consumes mechanical energy continuously, and something must keep replacing it. That something is the pump, and its job splits into exactly 3 parts. First, it must lift the liquid against gravity, from a suction tank to a higher discharge point. Second, it must push against pressure, from a vessel at one pressure into a vessel at a higher one. Third, it must pay the friction bill computed in Chapter 4, the loss that grows roughly with the square of the flow rate. Those 3 parts are easy to weigh in the wrong proportion. A pump that only had to lift liquid 10 meters might easily be delivering another 15 meters worth of energy purely to overcome pipe friction. On a long transfer line, friction is the dominant term, not the lift. Industry does not quote pump energy in joules, nor the resulting rise in pascals. It quotes head, symbol H, in meters, and head is the pump work divided by G. A length falls out because head is energy per unit weight of fluid rather than per unit mass. A pump delivering 30 meters of head would, in the absence of friction, raise any liquid 30 meters, water, gasoline, or sulfuric acid alike. That fluid independence is the whole reason the unit survives, because one number on a nameplate then describes the machine rather than its contents. Pressure behaves differently. The pressure rise follows the hydrostatic relation of Chapter 1, delta P equals rho GH, so the same 30 meters becomes a different pressure in every liquid, in proportion to density. With water at 998 kilograms per cubic meter, it is 2.94 bar. With an organic solvent at 800, it is 2.35 bar, about 20% less. Head is a property of the pump. Pressure is a property of the pump and the fluid together. Almost every pump in a chemical plant belongs to one of 2 families, distinguished by how they add energy. A centrifugal pump accelerates liquid outward with a rotating impeller and converts that velocity into pressure. It is the dominant workhorse. Simple, cheap, no valves, tolerant of solids, and continuous. Its defining behavior is that head falls as flow rises. Open the discharge valve wider, and the pump gives you more flow at less head. A positive displacement pump is the mirror image. It traps a fixed volume of liquid and pushes it out mechanically, through a gear mesh, a piston, or a flexing diaphragm, so its flow is nearly constant regardless of the pressure it must overcome. That is powerful and dangerous. Running against a closed discharge valve, it does not stall. It keeps trying to displace its volume, and the pressure climbs until something yields. It must never be operated against a closed valve without a relief device in the discharge line. Viscous, metering, and high-pressure duties go to positive displacement. Nearly everything else goes to centrifugal. A centrifugal pump does not have a flow rate. It has a pump curve, head versus flow, sloping downward because head falls as flow rises. The piping has a system curve of its own. The static head the liquid must be lifted through, plus the friction loss of Chapter 4 expressed as head, rising roughly with the square of the flow. The pump can only deliver a combination that lies on both curves at once, so the plant runs at their single intersection. That intersection is the operating point, and it is a property of the pump and the piping together, never of either one alone. This is the most useful picture in all of pump work. It tells you that you cannot simply choose a flow rate. You can only change one of the two curves and let the intersection move to wherever it goes. Everything on the next slide follows from that. Throttling changes the system curve, and a variable speed drive changes the pump curve. Two ways exist to move the operating point. Throttling a discharge valve adds friction, which steepens the system curve and slides the intersection left to lower flow. It is simple and instantaneous, and it is exactly what a control valve does. It is also wasteful, because the pump still produces high head and the excess is destroyed across the valve as heat. A variable speed drive instead moves the pump curve down. The scaling is captured by the affinity laws, the proportionalities relating a centrifugal pump's performance to its rotational speed. Flow scales with speed. Head scales with speed squared. Power scales with speed cubed. That cube is the entire economic argument for variable speed pumping. A 20% speed reduction removes roughly half the shaft power. Treat these as idealizations rather than guarantees. They assume geometric similarity and unchanged efficiency, so they are a first estimate. And one warning belongs here: throttle the discharge if you must, never the suction. Chapter 2 previewed a failure that Bernoulli made inevitable. Accelerate a liquid enough and its pressure falls to its own vapor pressure, and it boils. In a pump that happens at the impeller eye, where velocity is highest and pressure lowest. Net positive suction head is the margin, in meters of head, between the absolute pressure available at the pump suction and the liquid saturation vapor pressure, also absolute, at the operating temperature. Feed a gauge reading into this comparison and 1 full atmosphere, about 10 meters of water head, silently disappears from your margin. Available suction head comes from the plant. Required suction head is a property of the pump, published on its datasheet. Available must exceed required, with a design margin commonly of half a meter to a meter or more. Violate it and vapor bubbles form and collapse violently. Cavitation, with gravel in the pump noise, vibration, falling head, and impeller metal pitted away. The fixes raise the left side or lower the right, raise the suction tank, cool the liquid, or short and widen the suction line. The classic victims are pumps handling liquids already at their boiling point. Move a gas instead of a liquid and the job is the same, but the fluid is compressible, which changes everything downstream. The machines are graded by how much pressure they add. Fans handle ventilation scale pressures, blowers moderate boosts, and compressors real pressure ratios. The important physical difference is that compressing a gas raises its temperature, which is the first law from our thermodynamics series showing up inside a machine. A compressor therefore delivers hot gas that may need cooling before the next stage, and the work involved is genuine shaft work, the precious commodity Chapter 2 of this series insisted on. Large duties are therefore split into multiple stages with intercooling between them. The result is less work for the same pressure ratio and materials that survive. It is the same staged and cooled logic that governs interstage cooling in exothermic reactors, which is a useful reminder that these patterns repeat all across the plant. The chapter's code makes the comparison concrete. It intersects a quadratic pump curve with a system curve carrying 12 meters of static head. At full speed with the valve open, the pump delivers 101.8 cubic meters per hour at 24.44 meters of head, putting 6.77 kilowatts into the liquid. Throttle until the friction coefficient doubles, and flow falls by 17% to 84.7, while power to the liquid barely moves, 6.74 kilowatts, because the pump simply climbs its curve to higher head. 1.99 kilowatts, some 30% of the pump's output, is now destroyed in the valve. Slow the pump to 80% speed instead, and flow falls to 71.0 with 3.48 kilowatts of fluid power and nothing burned in a valve. Note honestly that flow fell further than the affinity law alone suggests, since 80% of 101.8 would be 81.5. The affinity laws describe the pump. The static head belongs to the system and does not scale at all. 5 chapters, 1 sentence each. Chapter 1 established fluid properties and the pressure that exists before anything moves. Chapter 2 turned energy conservation into the mechanical energy balance and Bernoulli's equation, which converts pressure, velocity, and elevation into one another. Chapter 3 introduced the Reynolds number and the laminar turbulent divide that decides which correlations apply. Chapter 4 priced friction in pipes and fittings and showed how sharply diameter controls it. Chapter 5 supplied the machine that pays the bill and matched it to the circuit. The arc does not end here. Every chapter has been an instance of one pattern, a flux equal to a coefficient times a driving force, and that same structure carries into heat transfer, a series planned next, where the driving force is a temperature difference, and into mass transfer planned after it, where it is a concentration difference. Where to go next? Our chemical engineering introduction series for the unit operations these flows serve. Chemical engineering thermodynamics for the property models behind vapor pressure and compression, and process informatics introduction for the data layer built on it. Thank you for learning with us.